Hi, in this video, we will discuss how to solve the non-homogeneous part for the second order ODE by using the method of undetermined coefficient. In this case, you have non-homogeneous ODE where the right-hand side function here is not equal to 0. We can use the method of undetermined coefficient to solve this non-homogeneous problem. This method can be applied when the right-hand side function is equal to exponential function, polynomial function, the multiplication between exponential and polynomial function. So when you have the alpha equal to real number, for example alpha equal to 5, then in this case you have exponential 5x. If your right-hand side is equal to exponential 5x, we can solve it using the method of undetermined coefficient. When your alpha is equal to some imaginary number, for example 3i, then the exponential is in 3ix, which can be linked to the cos and sine using the Euler Formula, which is equal to cos 3x plus I sine 3x. If the alpha is equal to negative 3i, then you have exponential negative 3ix. So in this case, you have the cos 3x minus I sine 3x instead of positive here. So you can see that the exponential function can be linked to cos and sine function, where the cos function is the real part for the exponential function, and the sine function here is the imaginary part for the exponential function. This means that beside the exponential and polynomial function, so if you have cos and sine function, we can also use the method of undetermined coefficient to solve the problem. For the polynomial function, n here refers to the degree. So when n is equal to 0, it means a constant. When n is equal to 1, then you have a coefficient multiplied with x. When n is equal to 2, you have second coefficient multiplied with x squared. When n is equal to 3, you have a3x cubed and so on. So this is degree 0, degree 1, 2, and so on. For example, if the polynomial function is equal to 8 in this case, then from here you know the degree is equal to 0, because polynomial function degree equal to 0 is a constant. If your right-hand side function is exponential 5x multiplied with 8x, then from here we can extract the alpha equal to 5, and your n instead of 0 it should be 1. The general formula for the polynomial function with degree 1 is equal to a1x plus a0. If the polynomial function is equal to 8x power of 2 plus 3 here, based on the highest power, which is equal to 2, therefore we can say the degree is equal to 2. And the general formula for the polynomial with degree 2 is equal to a2x squared plus a1x plus a0. You might also have alpha equal to complex number. For example, let the alpha equal to 5 minus 3i, which is a complex number. In this case, you have exponential 5 minus 3ix, which can be separated into exponential 5x multiplied with the exponential negative 3ix. And from the Euler formula, exponential negative 3ix is equal to cos 3x minus I sine 3x here. So in this case, your real part is equal to the exponential multiplied with the cos function, and your imaginary part is equal to the exponential multiplied with the sine function. In simple, we can use the method of undetermined coefficient to solve the second order non-homogeneous problem here if the right-hand side function is either exponential, polynomial, cos, sine, exponential cos, and exponential sine. So if your right-hand side function consists of this, then we can solve it using this method. So in general, to apply the method of undetermined coefficient to solve non-homogeneous second order problem like this. So the right-hand side function here can be equal to the multiplication between two functions. So you have the exponential function and also the polynomial function. When the alpha is equal to imaginary number, you know that you can link the exponential function to sine and cos. So any mixture between the exponential, polynomial, sine and cosine function, we can solve it using the method of undetermined coefficient. In this method, we propose the possible particular solution depend on the right-hand side functions. Previously, we have learned that the solution for the second order linear ODE with constant coefficient A, B, C here, so the solution is equal to the complementary solution plus the particular solution. We have learned how to solve the complementary solution previously, where we let the Rx here equal to 0. By solving this homogeneous ODE, we can obtain the complementary solution. Now we will learn how to find the particular solution based on the right-hand side function. So this method is called the method of undetermined coefficient. Based on the right-hand side function, which is the mixture between the exponential and the polynomial function, so we can propose the possible particular solution in this format. You can see that if your right-hand side function is equal to exponential alpha x, so the possible particular solution will be in exponential alpha x also. For example, in this case, you have a pure exponential function where the right-hand side function is equal to exponential negative 3x. Therefore, we can propose the particular solution equal to exponential negative 3x. Then you continue to check the degree for the polynomial function and propose the general polynomial function with the same degree. The general polynomial function with n degree is written in this format, where you have constant a0 plus a1x plus a2x squared until the maximum degree. Let's check the right side. What is the polynomial function here? Since the exponential function is multiplied with 1, so the polynomial function is a constant. Therefore, the degree for the polynomial function is equal to 0. So that your polynomial function here is equal to a constant 1. So if your degree is equal to 0, then you need to propose the Q0, which is equal to a constant A0. Therefore, we can substitute the Q0 equal to constant A inside. In this case, the right side function is equal to exponential negative 3x. When you compare to this format, your alpha is equal to negative 3 and your n degree is equal to 0 because you have constant 1 here. So from here you can propose your possible particular solution to be this format. So since your alpha is equal to negative 3, substitute inside, you obtain exponential negative 3x. So you can see the exponential part remain. Then you continue with the polynomial part. So the constant, okay, you need to convert to the general equation for a constant. So you can put a coefficient A to represent the constant. So this is what you propose for the particular solution. So you have undetermined coefficient A in this case. Later you will learn how to find this unknown coefficient. At the moment, you need to learn how to propose the possible particular solution based on the right-hand side function here. In this case, the right-hand side function is a pure sine function. So you have sine phi x here. So what is the possible particular solution that you should propose? So from the Euler formula, we know that the sine phi x here can be linked to the exponential function by using this formula. To have positive sine phi x, let's write it down here. So you see the sign is at the imaginary part. So from this formula, so if you have positive here, then this term will become positive also. So the cos x here, you need to replace by cos phi x. And your exponential here become positive phi ix. With that, the exponential I phi x is equal to cos phi x plus I sin phi x. So you have learned complex number before. Let the complex number equal to z here, where z is equal to a plus bi. Let's assume z equal to 3 minus 2i. So if you want to find the real part for the z, then we take the real part for the z, give you the real number only, which is 3. So if you want to find the imaginary number for the z, it will be equal to the b, which is equal to negative 2 in this case. Therefore, when we take the imaginary part for the exponential I phi x here, so you will take the sin phi x, which is at the imaginary part. So if you take the real part of the exponential I phi x here, then it will be equal to the cos phi x. Since the sin phi x is equal to the imaginary part of the exponential phi ix, therefore we can propose the particular solution equal to the exponential phi ix. And later on, you know that the actual particular solution is equal to the imaginary part of this. So for the right hand side function, the sin phi x is multiplied with 1. Therefore, you know that 1 is equal to the polynomial function with degree equal to 0. So the general formula for a constant, okay, we can use a to represent it. So we can propose the yp equal to ae phi ix, and the actual yp is equal to the imaginary part of it. Similarly, if the Rx is equal to a cosine function, then by forming the Euler formula where the exponential I6x is equal to the cos 6x plus I sin 6x, and you see that the cos 6x is at the real part of the exponential I6x. With that, we can propose the possible particular solution to be the exponential 6ix here. So exponential 6ix is in terms of the cos and sine. To find the cos only, later you need to find the actual yp solution at the real part. Since you only have cos function in your right hand side, therefore you can imagine the polynomial function to be the 1. So the polynomial equal to 1 is the polynomial with the degree n equal to 0. The general formula for a constant, we can just substitute q0 equal to a here. With that, the possible yp solution is equal to this, and you need to find the actual solution in the real part. So you can see that if the right hand side function is either sine or cosine function, then your alpha will be in the imaginary number. With that, you obtain the exponential in the imaginary number like this. Based on the Euler formula, the sin x is located at the imaginary part. Therefore, you need to find the imaginary part for your actual yp solution. Cos x is located at the real part. Therefore, you need to find the real part of the yp to obtain the actual solution. If your function is in sine or cosine function, we can use the first option, which is in the exponential format, to solve the particular solution. Instead of the option 1, there is another alternative, which is the option 2 here. So for the sin phi x here, you can propose the particular solution equal to c cos phi x plus d sin phi x. If the right hand side is equal to cos 6x, then we can propose the particular solution equal to c cos 6x plus d sin 6x. You can obtain the same answer for the particular solution by using these two options. Therefore, both options are acceptable in this study. In this study, you should focus to master both options, because in the engineering application, the exponential format as well as the trigonometric format are useful and important. In this example, the right-hand side function is equal to the exponential function multiplied with the cosine function. From the Euler formula, we know that the cosine function can be linked to the exponential function in this format. So you have exponential I6x equal to the cos 6x plus I sine 6x. And the cos 6x is equal to the real part of the exponential I6x. If you multiply the exponential negative 3x with the exponential I6x, then you will obtain exponential negative 3x multiplied with the cos 6x plus I sine 6x. So you can see that exponential negative 3x cos 6x is located here, which is the real part of the exponential negative 3x multiplied with exponential negative I6x. Don't forget the bracket. With that, we can convert the multiplication between the exponential and cosine function here into this format. From the right-hand side function, the polynomial is equal to 1 in this case. Therefore, the degree for the polynomial is equal to 0. Therefore, the n is equal to 0 in this case. So Q0, the general formula will be a constant a. To simplify the calculation, we propose the particular solution using this exponential function. After you solve the YP solution later, you need to find the real part, because you know that the actual solution is located at the real part. In simple, if you have this right-hand side function, to propose the possible particular solution, you need to check the power for the exponential. And the cosine 6x here is linked to the exponential I6x. Therefore, we can multiply the exponential here to obtain the coefficient for the alpha here equal to negative 3 plus 6i. Therefore, the alpha for the particular solution is in this format. And you need to multiply it with a constant a, because the polynomial function here is a constant 1. This is incomplete solution yet, so after you obtain the YP solution in this format, you need to consider the cosine is in the real part for the exponential. Therefore, you need to proceed to find the solution in the real part. So this is the first option to propose the particular solution. For the second option, the exponential negative 3x remains. For the cos 6x, we propose the general trigonometric function equal to the c cos 6x plus b sin 6x. Both options are acceptable in this study. You should focus to master both, as they are useful in the engineering application later. How if we change the right side function equal to the exponential multiplied with the sin 6x here? So from the Euler formula, you know that the sin 6x is located at the imaginary part. So take the imaginary part of the exponential I6x, give you the sin 6x. Therefore, from here, you can propose your particular solution based on two functions. One is the exponential function, another is the polynomial function. So in terms of the exponential function, you have the exponential negative 3x, and the sin 6x can be linked to the exponential I6x. And we don't write the imaginary part here to simplify the calculation, where we will consider the imaginary part later. So your actual YP, okay, you need to consider the imaginary part later. So from here you should know your polynomial function is equal to 1. So the general formula for the constant is equal to A here. By doing this, we success to form the particular solution for this problem. So this is the first option. For the second option, we can link the sine and cosine function to this trigonometric function. So the exponential negative 3x remains in the particular solution, and the sine 6x can be proposed in the trigonometric format, which is A. So since we have constant A here, let's use other parameter. So we have a C cos. Okay, so this one is 6x. You need to put 6x inside plus D sine 6x. So you can see over here, based on the sine 6x, we propose C cos 6x plus D sine 6x. So the constant one here, we can propose, let's say, the constant A. So you can see that the constant A can be multiplied inside. So to obtain a new constant, and A multiplied with the constant here, you obtain new constant. Therefore, we can further simplify it to this format. Let's continue. If your right-hand side function is a polynomial function without the exponential function, so in this case, your alpha must be equal to 0 so that the exponential function can be cancelled to 1. Based on the polynomial function here, the highest power is equal to 3. Therefore, we know that the degree is equal to 3. Therefore, there is no exponential function in your particular solution, and the polynomial function is in the degree 3. So you can write the general polynomial formula, which is equal to ax power of 3 plus bx squared plus cx plus d. What if you replace the 4x squared here into 4x power of 4? So if you check the highest power now is equal to 4. Therefore, the degree will change to 4. Then you will obtain Q4, where the general polynomial function should be written into ax4 bx cubed cx squared dx plus e. So this is the general formula for the polynomial function with degree 4. In this example, the right-hand side function is in the multiplication between the polynomial function with degree 1, because the x power of 1 here. So another function is exponential function, where the alpha is equal to negative 3. Therefore, we can propose the particular solution equal to exponential negative 3x, and the general polynomial function with degree 1 is equal to ax plus d. If the polynomial here is 6, then the degree will be 0. So the general polynomial equation here, you can write it equal to a only. If the polynomial function here is changed to 6x squared, then the degree is 2. So the general formula for the polynomial function here will be equal to ax squared plus bx plus c. So this is how you propose the particular solution. In this example, you have the right side function equal to exponential function plus the polynomial function. Previously, we have learned that if the right side function is given in polynomial function only, so based on this function, we know that the polynomial is in the degree of 3. Therefore, the general formula for the polynomial function is equal to ax power of 3 plus bx squared plus cx plus d. So this is our particular solution. You also learned that if your right side function is equal to exponential negative 3x, so based on this, your alpha is equal to negative 3, and the polynomial function is 1, therefore we can use constant to represent it, and the exponential function remains. So this is how we propose the particular solution for this kind of function. In this example, you can see that the right side function now is the combination of the exponential function, which is R2, plus the polynomial function, which is R1. So what is the YP particular solution for this kind of right-hand side function? We can use the linear superposition to solve this problem. So if you found that the right-hand side function is the linear combination or the summation between some function that you know, okay, with other function, then you can see that the Rx here is equal to R1 plus R2. So the YP solution here will be equal to YP1 plus YP2 as well. Therefore, your YP solution is equal to this plus this. So you can see that from the polynomial function here, your YP solution is given in this, and for the exponential function here, you obtain another YP solution. So the total YP solution will be equal to YP1 plus YP2. So this is what we can propose. So we can propose the particular solution equal to the YP1 plus the YP2 here. You need to be careful with the coefficient. Make sure you don't use the same symbol for different coefficients. So for example, in this case, you are using the same symbol for A here for different coefficients. Therefore, you should change the A here to another symbol. Let's change it to E. What if you add another function to this? For example, you add sine phi x. So you have additional R3 function in sine format. So for the sine phi x, previously we learned the particular solution can be written into exponential format. So in this case, the angle inside is phi x. Therefore, the exponential here, the alpha is equal to I phi x. So don't forget, the constant 1 here can be represented by A. So since we have used the A coefficient, so A, B, C, D, E have been used, so we use the coefficient F here. So you can propose the particular solution equal to Fe I phi x for this term. Besides the exponential format, we can also use the trigonometric format to represent the sine function here. These two formats are acceptable for the particular solution tree here. Since your new right hand side function now is equal to R1 plus R2 plus R3, by using the linear superposition, we can propose the particular solution Yp equal to Yp1 plus Yp2 plus Yp3. So you need to add the Yp3 inside here. So this is our new particular solution. If you add more terms to the Rx function, for example R4, R5 and so on, then similarly we can add the Yp4, Yp5 and so on to the equation. So you can see that the Yp equation is very long sometimes. As an alternative, we can solve it separately. So for example, we can focus on the R1 and solve for the corresponding Yp1. Then once you obtain the Yp1, we will focus on the R2 and eliminate the other R. By doing this, we will obtain the Yp2 only. Then you continue with the R3 to obtain the Yp3, R4 to obtain the YP4, R5 to continue to obtain the YP5, and so on. Once you obtain all the solutions separately, then the total particular solution will be the superposition of all the solutions here. Try to solve this example. So you see the right hand side is in the summation of exponential function and two sine functions. Therefore, the right hand side function is equal to R1 plus R2 plus R3 here. Based on each right hand side function here, you propose the particular solution. For the R1, you have 5 exponential negative 6x. Therefore, the particular solution is equal to AE negative 6x. For the second R2, then the YP2 means the second particular solution due to R2 is equal to A cos 8x plus B sin 8x. Or we can write it in the exponential format. So sin 8x here give you exponential I 8x. And don't forget the constant. You need to be careful. You should avoid the same symbol for different coefficients. Therefore, we change this to B and change this to C. And this will be D. Lastly, the third particular solution due to the R3 will be equal to, so based on this, you have a sin 10x. Therefore, it can be written in E cos 10x plus F sin 10x. Or we can write this in the exponential format. So sin 10x is also equal to exponential I 10x. And don't forget the constant. If you use the exponential format to represent the sine function here, then you need to consider the imaginary part. So your YP actual for case 3 and case 2 here will be equal to taking the imaginary part of the YP for case 2 and case 3. Since you know that the Rs is equal to R1 plus R2 plus R3, therefore your YP will be equal to YP1 plus YP2 plus YP3 as well. This approach is called the linear superposition. So far, you have learned how to propose the particular solution in this format. So by using the method of undetermined coefficient based on the right hand side function, which is in either exponential, sine, cos, or the polynomial function, then we can propose the particular solution in this form. Also, we know that for the second order linear ODE with constant coefficient ABC, the total solution will be equal to the complementary solution plus the particular solution. So previously we learned how to obtain the complementary solution by consider the Rx here equal to 0. With that, you should obtain this equation, and we can use the characteristic equation to find the root for the homogeneous ODE. So from here you obtain AM squared plus BM plus C, which is equal to 0, and then you can solve for the M1 and M2. So for the second order ODE, you should have two roots. Based on the M1 and M2 roots that you obtain, we can separate it into three cases. So for the first case, you obtain the M1 and M2 in the real number and both of them are different. For example, let the m1 equal to 2, m2 equal to 3 in this case. So this is the first case. In the second case, you might obtain the m1 and m2 in a pair of complex conjugate or the complex number, and you see m1 is not equal to m2. For example, here you obtain 5 plus 6i for the m1, and for the m2 here you obtain 5 minus 6i. Both case 1 and case 2 has linearly independent solution. Therefore, we can write the complementary solution in such linear combination format. In the third case, you might obtain the m1 here equal to m2. So this is known as the repeated root. Without the treatment, you see the solution here and the solution here are linearly dependent. In this case, you only have one useful independent solution. Therefore, to obtain another missing independent solution, you need to multiply the independent variable to one of the solutions. By performing this treatment, now we success to obtain two independent solutions. So bear in your mind, to solve the complementary solution, we need to ensure the y1 and y2 solution here, both of them must be linearly independent. So if you see the solution is in linearly dependent, like the case 3 here, we need to perform a treatment by multiply the solution with independent variable. So for example, in this case, initially exponential mx is linearly dependent to the second solution here. So we perform the treatment by multiply one of the solution with the independent variable. By doing this, now we obtain y1 and y2, both of them are linearly independent. We should always solve the complementary solution first before we proposing the particular solution. First of all, we solve the homogeneous part of the ODE first, where the right hand side is equal to 0. So you can obtain the root from the characteristic equation, and then you can form the complementary solution. From the complementary solution here, you know the corresponding coefficient for the m1 and m2. Next, you continue to solve the non-homogeneous part of the ODE, where the right hand side is not equal to 0. Based on the right hand side function, we can use the method of undetermined coefficient to propose the particular solution. From the particular solution here, we can obtain the coefficient alpha from the exponential term, like you obtain the m1 and m2 coefficient from the exponential term here. The coefficient m and coefficient alpha must be compared in order to confirm this particular solution, whether it's good or not good. If the coefficient alpha is not equal to the root m1 and m2, for example, the alpha is equal to 7 in the particular solution, and when you compare to the complementary solution, is different with the m1 and m2. Therefore, the particular solution and the complementary solution are linearly independent. So no treatment is needed, and we can use this particular solution. In the second case, you might obtain the coefficient alpha equal to one of the roots. For example, alpha equal to m1 here, and the m1 is not equal to the second root. For example, if the particular solution here, you have the alpha equal to 6, then this will be equal to one of the root here. Or when the alpha is equal to 2 plus I, then it will be equal to one of the root for the complementary solution. Without the treatment, your particular solution and the complementary solution will be linearly dependent. For example, in this case, you have second order ODE where the right hand side is not equal to 0. So this is non-homogeneous case. To solve this problem, you need to solve the homogeneous part first by let the right hand side equal to 0. So you form the characteristic equation for this. You should obtain m squared minus 11m plus 30, which gives you 0. So from here, you obtain the root. So after you calculate, you should obtain the root 1 to be 6, root 2 to be 5. With that, you can form the complementary solution, which is equal to the constant 1 multiplied with exponential 6x plus constant 2 multiplied with the exponential 5x. Since the solution 1 and solution 2 here are linearly independent, therefore no treatment needs to be done in this case. So this is our complementary solution. So we continue by consider the non-homogeneous part. So when you look at the right hand side, is equal to the exponential 6x. With that, we can propose our particular solution. So the possible solution for this is equal to exponential 6x remain. So you have a constant 1 here. So the general formula for constant 1 is equal to 8. To check whether the particular solution here is good or not, we need to compare the complementary solution and particular solution. So when you compare, you see that the particular solution here is in the same format with one of the complementary solution. So in this case, we say that the particular solution is linearly dependent to the complementary solution. So we cannot propose this format for the particular solution. There is typo in this equation, so you should have y here. So if you substitute y is equal to a exponential 6x inside here, and take the y prime of this to obtain 6a e 6x. So you can substitute inside here, and lastly your y double prime will be equal to 36a exponential 6x. So you can substitute the y double prime inside. Then supposingly, you should obtain the right hand side equal to exponential 6x when you substitute this particular solution. Once you substitute y prime and y double prime and compute the left hand side, you should obtain 0, which is not equal to the right hand side. Therefore, we can say that the particular solution that we propose in this case is not correct. This is because the particular solution that you propose is linearly dependent to the complementary solution. And previously, you should know the complementary solution will make the right hand side equal to 0. So we should avoid the complementary solution linearly dependent to the particular solution here. We should make sure these two solutions, both of them are linearly independent. So in this case, we need to perform the treatment to the particular solution. This can be done by multiply the solution with the independent variable. After the treatment, your particular solution now consists of x exponential 6x, which is linearly independent to the y1 solution and y2 solution here. Therefore, we can continue with this particular solution. In simple, if you propose the particular solution and you see the exponential term here is similar to one of the solutions, then you need to multiply it with x, which is the independent variable for the treatment. By doing this, your yp and yc here will be independent to each other. For the third case, your coefficient alpha will be equal to these two roots. For example, let's change the second order ODE into y double prime minus with 12y prime plus 36y equal to exponential 6x. To solve this problem, we need to solve the homogeneous part first by let the right hand side equal to 0. So we can form the characteristic equation. So y double prime will change to m squared, y prime will change to m, and the coefficient is negative 12. Lastly, you have the 36. By solving this using calculator, you can find the root to be equal to 6. Since both of them are the same, therefore this is repeated root case. And you can find your complementary solution equal to C1 exponential 6x and C2 exponential 6x. And these two solutions are linearly dependent. So you need to perform the treatment multiply with x, which is the independent variable. By doing this, the y1 and y2 here are linearly independent now. So this is your complementary solution. We continue to solve the non-homogeneous part by refer the right hand side equal to exponential 6x. So from here, you can propose the particular solution to be AE6x. To validate this particular solution, you need to compare to the complementary solution. So when you compare, you see that these two solutions are linearly dependent, which is bad. This is because when your YP is same with one of the complementary solutions here, it will make the right hand side equal to 0. So we need to make treatment to the particular solution by multiply it with the independent variable. So we check again for this solution, and we see this solution is also same with the solution here. Therefore, we say the particular solution is still linearly dependent to the complementary solution to make the right hand side equal to 0. And we continue to multiply x to give x squared. Now you see that the particular solution here is no longer linearly dependent to the complementary solution. Therefore, we say the yp and yc now are linearly independent after the treatment with x squared here. Therefore, this is our particular solution. In summary, we need to always check the particular solution with the complementary solution in order to validate the particular solution. If the particular solution here is not the same with the y1 and y2 solutions, then we say they are linearly independent and no treatment is needed. However, if you see your particular solution is same with one of the complementary solutions here, where the alpha here is equal to m1. So in this case, you need to perform the treatment by multiplying your particular solution with the independent variable. Lastly, if you have the particular solution where the alpha is equal to m1 and also equal to m2, so in this case, the complementary solution here will be linearly dependent to the particular solution. In this case, you need to perform the treatment by multiplying the particular solution with x squared. By doing this, the particular solution now has different format with the complementary solution. With that, we say the yp and yc are linearly independent now. So this is the way to validate the particular solution. So you should know when you should perform the treatment, like these two cases, and when you do not need any treatment, like this case. In simple, if you found the complementary solution has the similar exponential function or similar solution like the particular solution, so in this case, you need to perform the treatment by multiplying either the independent variable x or the x squared to the particular solution. In this example, we are going to solve this second order ODE, where the right hand side is an exponential function. So for this problem, your solution will be equal to the complementary solution plus the particular solution. We need to solve the complementary solution first. So we look at the homogeneous part by let the right hand side equal to 0. And from here we can form the characteristic equation where your y double prime will change to m squared, y prime will change to m, and your y will change to 1. So by using calculator, you can solve the root m, which is equal to 2 and 1 here. Your complementary solution is in the exponential function, so you can substitute the root m inside to obtain the first solution and second solution. Since these two solutions are linearly independent, therefore they can be combined in such a linear combination. So this is the final answer for the complementary solution. Then we continue to solve the non-homogeneous part. Based on the right hand side function, which is equal to exponential x in this case, we can propose the possible particular solution. So it should be equal to constant a multiplied with exponential x. In order to validate this particular solution, we need to check with the complementary solution. So you see this format is similar to one of the solutions here. Therefore, we can say that the particular solution is linearly dependent to the complementary solution, which is bad. So we need to perform the treatment. So in this case, you multiply with x, which is the independent variable. And you check again with the complementary solution, and now we see the particular solution is linearly independent with the complementary solution. Therefore, we can continue with this solution. From here, you obtain the particular solution equal to ax. Then you continue to differentiate it. So we constant the ax and differentiate ex, you obtain ex. And then we continue to constant the ex and differentiate the ax, you obtain a only. So this is your yp prime. Let's differentiate again to obtain the yp double prime. So when you differentiate the ex, you should obtain the ex plus aex. Then when you differentiate aex, you should obtain aex. So these two terms can be added up to obtain 2aex. With that, you obtain this solution. Next, we need to substitute the yp prime and yp double prime into this equation. So you obtain the yp prime and yp double prime. So after you solve the left hand side, you should obtain this equal to exponential x. So after you substitute back the yp prime and yp double prime, you should obtain this equation. So you collect the term for xex here, where a minus 3a plus 2a give you 0. So these three terms can be cancelled. Then you continue to collect the term for aex. 2 minus with 3, you shall obtain negative aex. Then you can continue to compare the coefficient for the exponential x. So when you compare the coefficient, on your left hand side you have negative a, on your right hand side you have 1. So rearrange it, you obtain a is equal to negative 1. And previously, your yp is equal to ax ex. So substitute negative 1 inside, you shall obtain negative x ex. So this is the final answer for your particular solution. Once you obtain the complementary solution and the particular solution, substitute inside this equation, and this is the final answer for the total solution. In this example, you have a second order ODE with constant coefficient, and your right hand side is a sine function. You are going to find the y with respect to x, and we know that this solution is equal to the complementary solution plus the particular solution. Let's solve the complementary solution first by looking at the homogeneous part. In this case, you let the right hand side equal to 0, and your complementary solution will be in the exponential format. To find the root for the m here, you can form the characteristic equation. So y double prime give you m squared, y prime give you n, 6y becomes 6 here, and by solving this equation, you obtain the m1 and m2, which is equal to 2 and 3 corresponding. So when you compare these two solutions, both of them are linearly independent. Therefore, this is the final solution. Then we continue to solve the non-homogeneous part. By referring to the right hand side, you know that 4 sine 2x can be linked to the exponential by using the Euler Formula. And you can see that the sine term here is located at the imaginary part of the exponential I2x. Therefore, we can propose the particular solution here to be equal to the exponential I2x. And the polynomial is a constant here, therefore we can put a to represent the constant polynomial. For the ease of calculation, we will continue the calculation with this format. Later, after we solve the yp, then we will look at the imaginary part for the yp to find the actual solution. Therefore, the yp is equal to ae power of 2ix in this case. To validate this yp, you need to compare with the yc solution. So after you check the solution here and compare with the yp, so all the solutions here are different and they are linearly independent to each other. Therefore, no treatment is needed for the particular solution, and we can proceed with this. So you differentiate it with respect to x. The coefficient 2i here you need to multiply, so this is the answer. Then you continue to differentiate again, and the 2i here multiplied with 2i, you obtain negative 4. So this is the yp double prime and yp prime. Let's continue to substitute the yp prime and yp double prime inside the equation and compare the coefficient on the left hand side and right hand side. So you continue to substitute the yp prime and also the yp double prime inside the equation. And we can replace the 4 sine 2x by the 4 exponential 2ix using the Euler formula. As we mentioned before, to simplify the calculation, at this moment we don't consider the imaginary part yet. So after you complete all the calculations, then only we consider the imaginary part. Negative 4a here plus 6a give you 2a. Negative 5 multiplied 2i give you negative 10i. Then we compare the coefficient for the exponential 2ix on left hand side and right hand side. So we take out the exponential 2ix. The coefficient is equal to negative 10ai plus 2a will be equal to 4. From here we can obtain the a, where your a is equal to 4 divided by 2 minus 10i. And you can further simplify it into this. So you have a complex number for your unknown a in this case. So you can substitute the a inside the yp solution. So later you are going to find the imaginary part of this yp solution to obtain the actual yp. So you continue to substitute the a inside, and you are looking for what is the imaginary part of your yp. So from this format, it's hardly to see what is the real part and what is the imaginary part. Therefore, we continue the derivation until we get the format where you have the real part plus your imaginary part. This can be done by substitute the exponential 2ix equal to the cos 2x plus I sin 2x by following the Euler formula here. And then you multiply this term with the complex conjugate. At the top you have 2 multiplied with the 1 plus pi I, which is this term. So 1 minus pi I multiplied with 1 plus pi I, you obtain 1 minus 25 I square. I square is equal to negative 1. Therefore, the summation is equal to 26. 2 divided by 26, you obtain 13. Then you continue to multiply 1 with the cos 2x to obtain this. And 5i multiplied with the I sin 2x, you obtain negative 5 sin 2x. You continue to multiply 1 with the I sin 2x, then you obtain I sin 2x here. Multiply the 5i with the cos 2x, give you 5i cos 2x. And you collect the term for the imaginary part and the real part. So this is your yp solution. Our actual solution is located at the imaginary part for the yp. With that, we remove the real part, and this is the actual solution. So we rewrite it, so you should obtain this for your particular solution. Lastly, you can substitute the complementary solution and the actual particular solution into the formula here. So this is the final solution to solve this ODE. In this problem, you have the sine function on your right hand side, and you assume the particular solution to be the exponential format, where you know from the Euler formula the sine function is located at the imaginary part of this exponential format. Therefore, after you continue solving the yp, and you need to find the imaginary part which is located at this component, so this will be your actual solution. What if you change the right hand side to a cos function? So in this case, all the procedure will be the same, but your cost function is located at the real part for the exponential function. Therefore, after you complete the YP solution here, you need to consider the real part. Then you should obtain your particular solution is located at the real part, which is equal to this answer. In this example, we have the same problem here, and if your right side consists of sine or cosine function, there is another alternative to solve it. So instead of using the exponential format that we used previously, so in this case, our particular solution will be in the trigonometric format. So after you check the particular solution and complementary solution, all the solutions are linearly independent. Therefore, we can proceed with this and no treatment is needed. So you continue to differentiate to obtain the YP prime. Differentiate sine 2x give you 2 cos 2x. Differentiate cos 2x give you negative 2 sine 2x. We continue to differentiate again to obtain the YP double prime. So cos you differentiate, you obtain negative sine. Then you multiply the coefficient 2 with 2 here to obtain 4. Differentiate sine give you cos. So the coefficient 2 multiply with the negative 2 here. So you obtain negative 4. So we continue to substitute this information inside the equation. So substitute YP, YP prime, and YP double prime here. Then you should obtain this equation. So we continue to collect the term for the sine 2x. And the coefficient is negative 4c. Negative 5 multiplied with negative 2d, you obtain 10d. And lastly, you have 6c here. So you collect the cos 2x. And this is negative 4d. Negative 2 multiplied with 2c, you obtain negative 10c. Lastly, you have 6 multiplied with d to obtain 6d here. Then we compare the coefficient for the sine 2x. On the left hand side, this is the coefficient, and negative 4c and 6c here can be simplified into 2c. So on your right hand side, the coefficient is 4. We continue to compare the coefficient for the cos 2x. So this is the coefficient on the left hand side. On the right hand side, you have nothing, therefore is treated as 0 multiplied with your cos 2x to give 0 answer on the right hand side. Therefore, the coefficient is equal to 0. From here, you have equation 1 and equation 2. So, two equations to solve two unknowns c and d here. We can solve the unknown easily by using the Cramer rule that you have learned before. So, you should obtain your d and c coefficient to be this answer. So, we substitute back the coefficient inside the YP solution. Then you should get this answer. In this case, we do not use the exponential approach, therefore we do not need to look at the imaginary part. So compared to the previous exponential approach, you obtain the same answer. Both options, either is exponential approach or the trigonometric approach in this case, are acceptable in this study. You should master these two approaches because we use them a lot in many engineering applications. What if we change the question to cosine problem? Previously, to solve this problem, we used the exponential format where the real part of the exponential I2x is equal to cos 2x here. Instead of using the exponential format to solve the problem, we can use the trigonometric format to solve it. So after your differentiation, you should obtain the same YP prime and YP double prime. Substitute it inside the equation, you should obtain this. And in this case, your right hand side will be equal to a cosine function. When we compare the coefficient for the sine 2x, so this is the coefficient on the left hand side. On the right hand side, you don't have sine 2x. Therefore, the coefficient is 0, multiplied with the sine 2x. So this should change to 0. We proceed to compare the coefficient for the cos 2x. So this is the coefficient on the left hand side. On the right hand side, you have 4. So this should change to 4. So we can use the Cramer rule to obtain the d and c coefficient by taking these two equation. So you can see that we need to change this to 0, 4. This one as well, because you have 0, 4 here. So if you continue the calculation, you should obtain D equal to 1 over 13 and C equal to negative 5 over 13. So you substitute back inside the YP solution here, then you should obtain this result. Both trigonometric format or the exponential format should give you the same answer. We continue with the example 3a. So in this case, the right hand side is the multiplication between the exponential and the cosine function. So we solve the homogeneous part first by let the right hand side equal to 0. Then you can continue to form the characteristic equation. So from here you can solve the root m1 and m2 should be equal to a complex number. So your m1 is equal to negative 2 plus I and your m2 is equal to negative 2 minus I. Since the y1 solution and y2 solution here are linearly independent, therefore no treatment is needed. So this is your complementary solution. You can extract the exponential negative 2x to obtain this format, and the exponential format here can be further simplified to the trigonometric format. So this format is also acceptable. Let's continue for the non-homogeneous part. So in this case, your right hand side is in the exponential and cosine function. Cos x can be converted to the real part of the exponential ix, and the exponential term here can be multiplied to give you negative 2x plus ix. From the Euler formula, you can form this equation where the exponential negative 2 plus ix is equal to exponential negative 2x multiplied with the cos x plus I sin x. So you can see that the right hand side function here is located at the real part of the exponential function here. Therefore, we can convert this to the exponential function here. From the right hand side function here, we can propose the possible particular solution to be this. So there's a typo here. This should be same coefficient with this, where the power here is negative 2 plus I multiplied with x. And then you should obtain this. To validate the particular solution, you need to compare with the complementary solution. So when you compare the solution, it is similar to one of the solutions. Therefore, the YP solution that you propose is linearly dependent to the complementary solution. And we need to do the treatment by multiplying it with independent variable. So after the treatment, you obtain the particular solution equal to ax exponential. Now the particular solution is linearly independent with the complementary solution. We can continue to find the yp prime and yp double prime by using the differentiation. So you constant the ax and you differentiate the exponential, you should obtain this, plus you constant the exponential now and differentiate the ax, you should obtain a. We continue to constant this term and differentiate the exponential here, so the coefficient will multiply with this coefficient and you obtain 4 minus 4i plus I squared. So I squared give you negative 1. 4 minus 1 give you 3. With that you obtain 3 minus 4i, which is this term. Then you continue to constant the exponential term and differentiate the coefficient here to give you negative 2 plus I multiplied with a. If you differentiate this, you will obtain the same answer also. So these two terms can be added up to give you this final answer. Then we can substitute back this information to the equation here and compare the coefficient. After you compare the coefficient, you should obtain the coefficient a here equal to negative 1 over 2 multiplied with I. So this is the step to obtain the coefficient a. So you substitute the yp prime and yp double prime inside the equation here, and you compare the coefficient from the left hand side and right hand side. So by doing this, you obtain the coefficient a equal to 1 over 2i. By multiplying this with I divided by I, So I square at the bottom give you negative 1. Therefore you have negative here. So this is the final answer for your A. So we can substitute this to the YP solution. Exponential Ix is equal to cos x plus I sin x. Let's multiply the I inside the bracket here. You obtain I cos x and I square. So I square here give you negative 1. Since your actual solution is located at the real part of the YP, therefore you need to find the real part of the solution, which is equal to 1 over 2. So the negative here can be cancelled, become positive. So you have 1 over 2 x e power of negative 2x, which is this term, and multiply with the sin x. So this is the final answer for your particular solution. If the right hand side function here change to sine function, then instead of the real part, you have to find the imaginary part for the final answer. Then you should have negative 1 over 2 x e to the power of negative 2x multiplied with cos x. So this is the solution when you have sin x here. Finally, once you find the complementary solution as well as the particular solution, substitute it inside the total solution to obtain the final answer. In this example, we will solve the same problem by using the trigonometric approach instead of the exponential approach. Based on the right hand side function, the exponential negative 2x is remain in the particular solution, and the cos x here can be represented by the c cos x plus d sin x. So this is the possible particular solution. To validate the particular solution, we compare it with the complementary solution. So you can see that the particular solution here is similar to the complementary solution. So both of them are linearly dependent. Therefore, we need to perform the treatment by multiplying it with the independent variable. After you perform the treatment, then you success to obtain YP solution to be linearly independent to the YC solution. You continue to perform the differentiation to obtain the YP prime and YP double prime. Then you substitute this solution inside the equation here, where this is the YP, so this is the YP prime, and this is your YP double prime. So after you compare the coefficient for the left hand side and right hand side, you should obtain the coefficient C equal to 0 and D equal to 1 over 2. Then you can substitute the C equal to 0 inside and D equal to 1 over 2. So the final answer will be this. The total solution for this ODE is equal to YC plus YP. So you can substitute the YC solution inside and the YP solution inside, and this is your total solution. Let's continue with example 4. You have polynomial function in this example. By using the same procedure, we can solve the problem. First of all, we need to solve the homogeneous part first by let the right hand side equal to 0. Then you form the characteristic equation. So you should have m squared plus 4 give you 0. And you can find the root m, which is equal to 2i and negative 2i in this case. So your y1 and y2 are linearly independent. Therefore, this is the complementary solution. We continue with the non-homogeneous part by refer to the right hand side, which is equal to 8x squared here. So the polynomial function here with degree 2. Therefore, we can propose the particular solution to be a2x squared plus a1x plus a0, which is the general formula for polynomial with degree 2. You have no exponential function in the right hand side. Therefore, you can treat it to be exponential 0x to give 1. Therefore, you don't have exponential format in the particular solution. So we check the particular solution and compare it with the complementary solution. All the solutions here are different, and we can say it is linearly independent. Therefore, no treatment is needed, and we can proceed to differentiate YP to obtain the YP prime and YP double prime. Then we substitute back the YP and YP double prime inside the equation here and compare the coefficient. And you should obtain the A2 equal to 2, A1 equal to 0, and A0 equal to -1. So this is the solution for your YP. Lastly, the solution for the second order ODE. The total solution is equal to complementary solution plus particular solution. So you need to substitute the solution that you obtained previously inside. Then this is the final solution. In example 5, you have polynomial function multiplied with exponential function in your right hand side. We solve the homogeneous part first by let the right hand side equal to 0. So you form the characteristic equation to be m squared minus 4m minus 12 equal to 0. So from here you obtain your root 1 and root 2 equal to 6 and -2. So since these two solutions are linearly independent, therefore this is the final answer for complementary solution. We continue with the non-homogeneous part. So you have degree 1 for the polynomial function. So the general formula for the polynomial function is ax plus b. And then we remain the exponential for x. So this is your possible particular solution. Then you can continue to differentiate the yp to obtain the yp prime and yp double prime. Substitute inside the equation here for your yp, yp prime, and yp double prime here. Then after you compare the coefficient, you should obtain the coefficient a and b here. So you should obtain the a to be -1/12 and b to be -1/36. And this will be your particular solution. Both of the complementary and particular solution are linearly independent. Therefore, we can further substitute inside the total solution here to obtain the final result. In example 6, you have exponential function plus the polynomial function in your right hand side. First of all, we let the right hand side equal to 0 to obtain the homogeneous part. Then you form the characteristic equation. So m squared minus 4m plus 3 give you 0. And from here you can solve the root for m. And you shall obtain the m1, m2 equal to 1 and 3 here. m1 is not equal to m2 in this case. Therefore, no treatment is needed, and this is the complementary solution. We proceed with the non-homogeneous part, and you need to be careful in this case. Previously, all the time we have one function only. So in this case, you have summation of multiple functions. So we need to find the particular solution based on each function here. So for the first right hand side function, your function is 3 exponential 2x. Based on this, we can propose the particular solution to be exponential 2x. Since the constant is 3, so the general formula for a constant is 8. The second right hand side function is equal to 4x, which is polynomial function. Therefore, you can propose the second particular solution to be ax plus b. And you need to be careful, since the a symbol have been used in this case, therefore you need to change to other symbol. Let's use bx plus c. Then you compare the particular solution with the complementary solution here, and you see the solutions are different. Therefore, they are linearly independent and no treatment is needed. So on your right hand side is equal to R1 plus R2. Therefore, your YP solution will be equal to YP1 plus YP2 here. So this is the total particular solution that you have. This approach is called the linear superposition. We will continue to differentiate the YP to obtain YP prime and YP double prime, and substitute back inside the equation here for the YP, YP prime and YP double prime. By compare the coefficient on the left hand side and right hand side, then you should be able to obtain the coefficient for A, B, C here to be -3, 4/3 and 16/9. So the total solution is equal to YC plus YP. Substitute the solution here, then you should get the final answer. What if you change the right hand side function here by remove the exponential function here. From the linear superposition, you know that your particular solution is equal to your yp1 plus your yp2, where the yp1 is due to the 3 exponential 2x function and your yp2 is due to the 4x. Therefore, when you remove this component without perform calculation again, you know that this component will cause the yp1. Therefore, the yp1 will be removed as well. And the final answer is without the exponential answer here. What if you want to solve the following ODE with the additional summation of sine function and cos function here? Previously, from the right function 1 and the right function 2 here, we successfully obtained the corresponding particular solution, which is equal to yp1 and yp2. Since the R1 is added with the R2 here, so by using the linear superposition, yp1 will be added with the yp2 as well. Now you have additional 2 right hand side function, which is R3 plus R4 here. Therefore, you need to find the corresponding particular solution for yp3 and yp4. To find the yp3 due to the R3 here, so we can remove all the other right hand side function to obtain this equation, where you have 5 sine 6x on your right hand side and the left hand side here remain. Based on the right hand side function, we can propose the yp3 solution to be a sine 6x plus b cos 6x. So you use the same approach by differentiate yp3 twice and substitute inside this formula, compare the coefficient, you should be able to obtain these two coefficients. Then we successfully obtain the yp3 solution and you can include it inside by the summation. To find the yp4 only, we will just focus on the R4 function. So your R4 function is equal to 10 cos 50x in this case, and you can propose the particular solution to be a sine 50x plus b cos 50x. By differentiate the yp4 twice and substitute inside the equation, after you compare the coefficient, you should obtain these two coefficients. Then you can include the yp4 solution here with the summation. So if you add additional 2 right hand side function to the existing problem, then the total solution will be equal to this, where you have additional yp3 plus the yp4 here. Second order ODE is frequently used to solve the mechanical vibration problem or the electrical circuit problem. In this example, let's represent the second order ODE to be a mechanical system, where you have mass, stiffness and damping. Under the force, the mass will experience displacement. Based on the second order ODE here, right hand side is the force. So you want to know under this force acting on the system, which consists of the mass coefficient, damping coefficient and stiffness coefficient. So you want to compute y with respect to t. So in this case, y is the displacement due to the force, and you want to know what is the changes of the displacement over time. Previously, we successfully to solve this second order ODE to obtain the total solution here. To shoot the application here, we change the independent variable to t here. If we reduce the problem to 3 exponential 2t on the right side, then the corresponding yp2 solution will be removed as well. Based on the formulation here, you know that the right hand side function here is the forcing function. So your forcing function is equal to 3 exponential 2t that is acting to the system, and the coefficient here indicate the mass, damping and also the stiffness. So after you apply the force to the system, you obtain the yp1 equal to this amount. So this is actually the steady state displacement. Steady state here means the displacement will continue to occur as long as the force is continuously applied to the system. On the other hand, if you apply the second force equal to 4t only, then the corresponding yp2 will be equal to this. So you can see that if you apply force 1 to the system, then the system will experience the displacement which is equal to yp1. If you apply force 2 to the system, then the system will experience displacement yp2. What if you apply force 1 and force 2 simultaneously to the system? So in this case, what would be the steady state displacement? If the two forces are acting simultaneously, then the total force will be equal to force 1 plus force 2 here. By using linear superposition, we can obtain the particular solution due to this force. The total steady state displacement will be just equal to yp1 plus yp2. In this example, you have an electrical circuit which consists of the resistor, capacitor, and inductor. This circuit can be modeled by the second order ODE here, where the Q is the charge and the current, you should know IT is equal to dq over dt. E is the electrical supply, which is the voltage here. After we substitute the resistance, capacitance, and inductance inside the equation, you should obtain this. First of all, we solve the homogeneous part first by let the right hand side equal to 0. Then we can form the characteristic equation and solve the characteristic equation. You obtain the root equal to m1, m2 here. With that, you obtain the charge solution in the exponential mt, where your m is equal to negative 0.05t. And this is your Q1 and this is your Q2. To avoid linear dependent solution, you need to multiply t here, which is the independent variable. So this is the complementary solution. Then we continue to solve the non-homogeneous part, where the right hand side is equal to 40. Based on the right hand side function, we can propose the particular solution to be a constant A. Since the particular solution is linearly independent with the complementary solution, therefore we can proceed. Differentiate constant give you 0, so differentiate again, you should obtain 0 as well. Substitute the QP, QP prime, and QP double prime inside this equation. Since these two terms are 0, therefore you obtain 1 over 8q equal to 40. And after you substitute q equal to a inside, you can obtain the a equal to 320. Substitute the a into this, then you obtain the particular solution. With that, we success to obtain the total charge equal to the complementary solution plus the particular solution. Then you can continue to differentiate the q with respect to t in order to obtain the current. So you have success to obtain the general complementary and particular solution, where you have unknown constant C1 and C2 here. The unknown coefficient C1 and C2 can be found by using the initial condition. This initial condition can be obtained from this statement. It is mentioned that at t equal to 0, the switch is closed. Therefore, at t greater than 0, the charge as well as the current is no longer equal to 0. So when your switch is closed at t greater than 0, the voltage supply will cause the current and charge to flow through this electrical circuit. At the moment you close the switch, which is at t equal to 0, the charge and the current are still equal to 0. Therefore, from this initial condition, at t equal to 0, so you can substitute all the t equal to 0 here, then the charge will be equal to 0. With that, you success to form this equation. Then exponential 0 give you 1. So C2 multiplied 0 give you 0. So from here you have C1 plus 320 equal to 0. And you obtain the C1 equal to negative 320. By using the second initial condition, at t equal to 0, so you substitute all the t here equal to 0. Then your current will be equal to 0. So this will be equal to 0. With that, you success to obtain this equation. So exponential 0 give you 1, and then C2 multiplied 0 give you 0. Therefore, you should obtain this. And from here, you can substitute the C1 inside to give this equation. Solve it, then you obtain the C2 equal to negative. Then we can substitute the C1 and C2 inside the charge equation. You should obtain this. And you continue to substitute the C1 and C2 inside the current equation. Then you should obtain this. So this is the actual charge and current solution for this problem. In mathematics, we know that we can obtain the total charge equal to the complementary solution plus the particular solution. So this is your complementary solution and this is your particular solution. For the engineering application, we also call the complementary solution as the transient solution. And the particular solution is also known as steady-state solution. The complementary solution is the response due to the initial condition. On the other hand, the particular solution is the response due to the right-hand side function here, which is the forcing function. In this case, the electrical voltage supply from the battery or the generator are the forcing function. In simple, the transient solution here will happen in a short time. We will see at t approaching infinity, the exponential negative infinity here will become 0. On the other hand, the steady-state solution will remain as long as the right-hand side function here or the forcing function here remain. So you can see that for this system, when it operates for a long time, when t approaches to infinity, the transient component will become 0 and the remaining term will be equal to Qp. Therefore, in many engineering applications, it is more desired to find the steady-state solution compared to the transient solution. So if the question is changed to find the steady-state charge, so in this case, we do not need to include the complementary solution because the particular solution is the steady-state solution. So 320 is the solution. And differentiate it, you obtain the current equal to 0. So for the steady-state current, you will obtain 0. So far, you have success to obtain the charge and the current solution for the electric circuit here. You can continue to plot the charge in the blue line and the current in the red line here. Then you can continue to use this information for the data analysis. For example, let's assume we use this RLC circuit for battery charging. So you can see over the time the charge increase up to a certain level and then it stopped and saturated at the maximum level here. So this is the maximum level, which is around 320. And you see this is our transient region where the charge is still keep increasing. And the charge remain constant afterwards. Therefore, this is called the steady state region. By identifying these two regions, then we know the battery takes around 150 seconds in order to fully charge the battery. Now you should know the transient region here is mainly contributed by the complementary solution, while the steady state region here is mainly contributed by the particular solution. So if you think that 150 seconds is too long to charge a battery, if you want to reduce this further, what should you do? Since the transient solution here is mainly dependent by the complementary solution, which can be solved from the homogeneous part, where the right hand side is equal to 0. So it's mainly depend on these three coefficients. So by altering these three coefficients and tune it to optimum value, then you should be able to reduce this further. Previously, we said that the charge takes around 150 seconds to reach the maximum value. If you zoom in the current curve here, the current will increase initially and decrease to 0 at 150 seconds. This means that when the battery is fully charged, your current will stay at 0.
So you can ask more questions and perform the data analysis to get more knowledge about the system. The intention of this example here is to encourage the student to link the mathematical result that you obtain to the actual scenario, instead of calculate the solution but know nothing. Data analysis on a specific engineering problem requires certain knowledge on the subject. Therefore, data analysis like this will be out of the scope in this study. You will learn more about this in other engineering class.